Okay, so I might have bitten off a bit much um, for this project, but we'll see. We'll see how it goes today in class. So go ahead and open up this salinity project requirements and also this winds tipping bucket Excel sheet. And we might as well open up the PDF document for chapter 4. So we'll be referring to it. Okay, so in the assignment, I'm going to have you evaluate the salinity out at our site. And one thing I'm going to have you do is just run a little test with our given irrigation water to determine um, the leaching requirement. So I have this set up in that Python program to evaluate that, not any specific crop, um, just like putting water on and having the same amount of evaporation. Okay, and then I will look up your threshold salinity and B values for your crops, your proposed crops, which I think some people chose some interesting crops, but we'll look at that. Then we'll download the reference ET relative humidity and wind speed for 2024 from the Azimuth Weather Station in Coolidge, which is close to our site. And we need that to run the model. And then using the model, we'll set up an irrigation schedule and simulate the salinity with the model for your crops. So let's get started with determining the well water salinity. And okay, so we've just taken like a 20-minute or 30-minute break trying to find the salinity at the our property, the wells on our property, and we could find hardly anything, but we did find data from 1997 at Tweedy Road and Kleck Road, and we're over here on section 16, where the salinity was 1,600 milligrams per liter. And so that's what we're going to go with for our project. If anybody finds better data, let us know. But we just spent I'd say half an hour looking for salinities, having no luck, except that one well at Tweedy and Kleck. Okay, now we're going to use the program with that salinity. And what we're going to do is we're going to have a 15% leaching and a 30% or 0% leaching. And I honestly don't think that that's enough. Okay, so I shared with you the program. And I updated it. So if you copied it over to your own program, you're going to have to recopy it because there was a few problems in there. So we're using the salinity and ET model. And we're going to upload winds tipping bucket. So that's here in 4, and we'll download it and then upload it. And now it's called Winds Tipping Bucket 3. So if you've been downloading and it's now Winds Tipping Bucket 3, that's the one you have to use because that's the most recent one. So now we'll upload. And here's Winds Tipping Bucket 3. Open. Okay. And actually what I like to do is keep track of the numbers. It's just easier that way. Then you know what you did most recently. So I have all these simulation options. These aren't crops, they're just for estimating salinity. And so the two that work the best are this 4L 20 centimeter, 30 millimeter, 15% leach. So that's what I have right here. So it's actually going to run that simulation. So I have to run my functions and classes first. Okay, so that's set up. And remember, this is Jupyter Notebook, so we can run separate files and it remembers the different files. And now we can run it. Oh, very sad. We have a problem. Worksheet named Irrigation not found. Oh, okay. Well, that's a problem. Oh, okay. So I do have this irrigation worksheet here. So fortunately, yeah, and it's also here. So somehow I uploaded the wrong file. So I'll go back to sample data. I'll do upload. And here's 5. Okay, I'll try to run it again, and I'll put 5 up here. Okay, it worked.
So I think that how cute like conversion factor deal with the 1600 because that's almost like almost seawater.
No, seawater's 39,000. So we're 15 times lower than seawater. It might be that we have a unit conversion, but it did say 1600, right? And I think that's a reasonable salinity for Pinal County.
What I'm seeing, I guess that's the but
Because seawater's um yeah, 39,000 or 36,000, something like that, milligrams per liter. And we're down in the 1600 range. Okay, so if we look at our graphs, okay, this is running it for a year with 15% leaching. And you can see that the upper layer is at 1.5. the next layer is at 2.5, the next layer is at 4.3, and the next layer is at 7.6. And so that's decisiemens per meter. Remember, it's 640 times decisiemens per meter gives you your salinity in milligrams per liter. This is the nitrogen here, and this is the water content. So what it's doing is once the roots grow down to a layer is activated, and at the beginning, all the water is getting taken out of the upper layers. But once the roots grows down into 4 layers, I'm taking out 40% from the upper layer, 30%, 20%, and 10% from the first, second, and third, and fourth layers. So that's why once the roots go down, which is here, and you can see also in this graph, here's my root depth. So it grows down to the max after that certain amount of time. But what I'm mostly interested in here is that what's the steady state salinity if we're leaching at 15%? And so, and it takes a bit of time to equilibrate, but it eventually does. And actually, this agrees perfectly with if you do a calculation for salinity in each layer, it's the same. So we know this program is right. But what we need to do is we need to change our salinity to 2.4, because 640 times 2.4 would be 1600, I think, right? Approximately. Or maybe we could just divide 1600 by 640. 2.5. Okay. So if we go to the daily, and actually, first we have to go to the tipping page. And this 20 centimeter, 30 millimeter, 15% leach, that's using set 2, not daily 2. Okay. And so that's down here. Here's our irrigation EC. So if we go to daily 2,
Which column is irrigation?
F. What did you say the salinity was? 2.4? 2.5. Okay. So we're going to put 2.5 here for the daily 2. Yeah, and then we're going to fill down all the way down daily 2. Column F. It's 1 right now, and you're going to make it 2.5.
Just for daily.
Just for daily 2. Okay. I think, yeah, daily 2. All right. Okay, so now I'm going to upload that one to Wind's Tipping Bucket, or to the program. Here it is, Wins 5.1. Okay, and I'm going to call that I could swear I changed it to 3, but oh well. Okay. See, now our salinity is going up to 17.5 with 15% leaching. In the upper 2 layers, it's only going up to 7.5, but that's only down to 20 to 40 centimeters, the second layer. So this is really awful. So what we need to do is have more leaching. Okay, so let's do 30% leaching. So there would be 2 ways to do that. So let's open that. I have to start with 5-1 again. Okay, so the irrigation events are here. Yeah, this 4L 20 centimeters, 30 millimeters. We're putting on 35 millimeters each irrigation. So let's try putting on 50 millimeters each irrigation. So that starts at line 47 in the Excel file. Yes. In irrigation file. Well, I'm gonna fill it down the whole season, so there's a lot of irrigations. So all the way down to line 149. I'm gonna put on 50. 50 millimeters. I'm gonna come around and help you in case you need help. Okay, so we're back after another half hour of pain and agony. And we changed the project because it was so difficult for people to run the program. And uh anyway, I guess it's not user friendly. But what I did is I ran the program for irrigating for a year with 15% leaching, and our well water salinity is 1600 milligrams per liter. That's the best we could find. That's 2.5 decisiemens per meter. So here is the expected salinity in 4 layers: electrical conductivity and decisiemens per meter. Here's the upper layer, second layer, third layer, fourth layer. This And this program agrees perfectly with theory, so it's right. So if you put on 15% leaching, you can expect that your decisiemens per meter are going to be very high. And so this is only down to like, this is 0 to 20, 20 to 40, 40 to 60, 60 to 80. So I ran it again with putting on 67% leaching. So I applied 50 millimeters when I only need 30 millimeters. And I think this is reasonable for our conditions. But check your crops. Check your B value and your threshold salinity and your B value to see what your yield will be at these salinities. And remember, the first thing you need to do is you need to convert these values to saturated paste extract salinity, okay? So I'm gonna put that in bold. Okay, so is saturated extract salinity going to be higher or lower than these values? Lower, because it's saturated, so the salt will be diluted. And the chapter has information on how to convert from the salinity in the model, which is basically around field capacity, and saturated paste extract salinity. So then, so really, it's only going to be 2.5, 3.5, 6, or this one will be 2, 2.5, 3, 3.5. So anyway, so once you know your threshold, salinity, and B values for your proposed crops, which come from tables either in the text or in the FAO 56 document, then you can recommend a leaching level so that your salinity is acceptable for that crop. So if you know this is 67%, and actually you can also do these calculations from, yeah, so just use the book. You don't need to use this for these calculations. So let's look at this. So here's chapter 4. Okay. Here's the B values and threshold values. These are based on saturated paste extract salinity. And here's the calculation of salinity for each layer. You get exactly the same numbers as I got. 1.5, 2.5, 4.3, and 6.7. Before I changed it to 2.5 salinity instead of 1, these are the values you get with 1. So these are the final salinities in this graph. These are the equilibrium salinities. But these are higher. These are actually the 15% leaching. So if you use this technique, you'll get the salinity in each layer by assigning a leaching fraction. So do that. I'll put that in the text. Use example 4.6 to calculate your salinities. Okay. So then once you know the B values and you can calculate your salinities in layers and you convert to the saturated paste extract salinity, then you can estimate your required depth of irrigation for your crops based on what you previously used, in your economic analysis and in phase 1, week 1. You can calculate how much water is needed for your crops to also have the leaching requirement satisfied. Any questions? Great.